Okay, this is a video for our chapter 16 in our text, Renewable Energy. This is actually module 2, so there's a separate outline. This is the only chapter in this module. So let's take a look at this. Definitions are always a good thing to focus on for quizzes, although a couple of these are a little bit more advanced. These last two are more advanced, so I would reserve those for until we get into the material. But energy efficiency, biomass, and anaerobic are things you should, get a grasp on for your quiz. Then we get into the concepts. Some of the early stuffs on solar energy are pretty basic and would be okay to ask on a quiz. But you get into solar cells and this down here, this stuff is a little bit more advanced. Hydroelectric's pretty basic. Wind's pretty basic. Biomass, if you know the definition, you're good. This stuff here is, say, for more advanced. Geothermal's pretty basic, and hydrogen, that's just more advanced, and we'll talk about that at the end of the chapter. As always, know the advantages and disadvantages of the different types. It's always a useful thing to know, and your book does a good job with that. So let's take a look at the book real quick here. So this is the chapter, Renewable Energy. Starts off with a little bit of important stuff here, but then it goes into a bunch of stuff you're not as responsible for. So I just want to point this out. This is really amazing. 84% of all commercial energy in the United States is wasted, but half of that is a result of not being able to do much about it because of the laws of thermodynamics that we talked about, just how that energy is wasted in transition. But there is the other half that basically is just inefficiency, whether it be light bulbs or automobiles. Okay. So here it's showing you too that what percentage we use is non-renewable and stuff like that. Go back and look at the pie charts. I believe at the beginning of chapter 15, which shows you, renewable versus non-renewable. And I have a slide that talks about that too. He spends a lot of time now here talking about energy waste and smart grids and all of this. Feel free to read it for your own knowledge base, but there's not much in here that you're responsible for until you start getting to the different forms of renewable energy, and here you go. And he titles them as, what are the advantages and disadvantages of each of them. So solar energy starts out with these passive and active systems for just heating, and I'll talk about that. And then you get into using the heat of the sun to generate electricity. So that's no different than really using nuclear or coal in the sense that you're just going to create steam to turn a turbine. You're not burning anything, which is the advantage, but it's using the heat to create steam. Eventually, you'll get into producing electricity directly, which is the solar cells, which is where the advanced chemistry is, the photovoltaics or the solar cells. And we'll talk about that in detail. Advantages and disadvantages as always. There's hydroelectric. I won't spend much time on this. It's pretty basic, as is wind, so just read and follow along with that. But biomass is where we'll spend some time. There's differences in biomass. There's biodiesel. There's bioethanol. There's biomass energy from anaerobic. There's even solid biomass. I don't really cover that. But just read this and get a thorough understanding of the differences in the biomasses. There's a whole big section here on biodiesel, and there's the ethanol. We're using different plants that we can ferment and things like this to get ethanol. So all of this stuff is really important. Then you got geothermal. Once again, that's pretty basic. And then we get into the hydrogen economy, and I'll talk about this and some things here. Here's fuel cells that I'll talk about here. He talks about, net energy again, which was introduced in chapter 15 with the fossil fuels, advantages and disadvantages. So I'll talk about that, and then he just has a nice conclusion at the end. So let's jump into the slides here. So these are renewable energies, alternative energies. So what we're looking at here is things that aren't our traditional materials that we mine, the fossil fuels, the uranium for nuclear, stuff that's sustainable, okay, that can be reused over and over again. And here's a basic introduction of what I'll go through. I'll go in a slightly different direction, order than the book does. Okay, so our sun deposits 10,000 times the energy we use, okay? that's pretty amazing in itself. We should be harnessing that. It's basically free energy. Renewable energy is only about 15% of global energy consumption. And that's changing, and that's increasing quite a bit on a pretty rapid pace. So that might even be a little bit outdated. Most of it, though, is still from biomass. And that's because these developing countries use a lot of crude forms of biomass, just burning wood, burning dung, and those have environmental impacts. They're not good for health because of air quality. There are biomasses that are better, but a lot of the developing countries aren't using those, so I'll distinguish and we'll talk about that, what these better forms of biomass energy are. Some of these renewable energies, alternative energies, can be really, really attractive for undeveloped areas because imagine, a mountain town in which you can't get power lines to, can't get them electricity. Well, then just put up some solar panels right there in the town, generate the electricity right there, and then you just have to run lines through the town. You don't have to get power lines to them from the generator, wherever your generating station is. The last part of the introductions, I'll talk about the hydrogen economy at the end. And I'll talk about fuel cell in context with fuel cells, but I'll touch on all of these things as your book does, and I'll do it in the context of fuel cells. Okay, so hydroelectric is pretty basic. It's the most heavily used renewable resource, with potentially biomass being, used quite a bit also, but not all biomass is renewable, and I'll explain that when we get to the biomass section. Because just like wood, if you burn it faster than you're planting the trees, it's not renewable and sustainable. Okay, so we talked about that a little bit when we introduced the idea of, renewable and non-renewable natural resources. Hydroelectric's got ideal power generation, 80% efficient. But there are problems. There's ecosystem damage. A lot of people are taking down dams now because that's what you have to do when you make hydroelectric power. You've got to dam the water, and then you control the release of that water, and you just simply use the water to turn a turbine instead of burning something and heating it. So I forgot to silence my notifications. Migratory fish have problems. You get silt buildup behind the dam. So those are problems. That silt buildup can affect spawning grounds. Eggs that are laid in the bed of the river and things like that. As far as the U.S. goes, about 8% of U.S. electricity generation is hydroelectric. And this is just showing the basic idea of how it's done. Okay, so what you're going to have is your dam and have gates that control the release of the water, and there's your turbine down here that's going to turn as this water comes down. You can control this, and you've got your power. It's no different than using steam to turn a turbine. Now we just use water. This is world hydroelectric power. This is a little bit dated. This is 2011. So I'm not sure about any major changes that have happened since then, but I know China is big on hydroelectric. They've built some big projects. This shows a little bit more recent hydroelectric in the world. This was in trillions of BTUs. This one is gigawatts, and I don't know that conversion off the top of my head. But it looks like, total installed hydroelectric power capacity in top 10 countries in 2014. So this is kind of like the capacity. This over here is net power generation. So basically potential capacity implies your potential to generate hydroelectric. And you see that China now dwarfs the other countries. Here's just some pictures, and your slides are posted so you can look at these. I don't need to spend time on that. That's really all there is to say about hydroelectric. It's pretty simple. Let's talk about biomass. I've got a definition from the Biomass Energy Center in the UK. Biomass is biological material derived from living or recently living organisms. In the context of biomass for energy, this is often used to mean plant-based material, but biomass can apply equally to both animal and vegetable-derived material. Okay? So, as far as its chemical composition, going to have a lot of carbon. I mean, carbon is the backbone for building living materials. That's the organic chemistry. It's the backbone for building, the structures of carbohydrates and fats and proteins and nucleic acid. We are, largely built on a backbone skeleton of carbon. All living things are. And then we have constituents, other important constituents like hydrogen, oxygen, nitrogen, sulfur, things like that, and various earth metals. So that's all going to be part of the biomass when it dies. So they actually derive the energy directly or indirectly from the sun. I mean, that's ultimately where most of our energy comes from. We list these different energy sources, and I think I even mentioned that solar drives many of them, like the hydroelectric, because solar drives the hydroelectric cycle, the hydrologic cycle. So plants capture that sun, and then animals eat it. We generate waste from it, so all of it really comes from the sun. Any accumulation of biological materials, and you can see a lot of them can be waste materials. And if we're using waste materials to generate energy, that's a good thing because we're cutting down on our waste. What you don't want to do is use, precious crops and important plants for generating energy. Is it renewable? This is the question. As long as you're using waste products or you're using it at the same rate at which you're replenishing it, it is renewable. But lots of times, biomass can be non-renewable. A solid can be burned or converted to liquid or gas. Liquids are key for transportation, so we tend to focus on liquids. We go to a station to fill up with a liquid fuel. So this is where the ethanol and the biodiesel comes in. Solids aren't going to be much use to us for transportation. So let's look at the difference in these now. It can be a fuel or an additive. So ethanol can be burned as a fuel. In this country, we only use about E10, which means 10% ethanol. But in countries like Brazil, they use like 85% ethanol. So effectively, the gas part is almost like the additive. So we get ethanol, the difference between these two. You should be able to distinguish between these two. Obtained from fermenting biomaterials like sugars. Okay, so you get this from corn, sugarcane, etc. And we ferment them. So basically, you put them in vats with, microorganisms. You allow them to ferment, and they produce ethanol. Biodiesels, basically chemical reactions as opposed to biological. Here, this is the fermentation is a biological process. These are chemical reactions, and we'll start with different things. We'll not start with sugars. We'll start with fats. So seed oils, animal fats. Biodiesel is cleaner burning than fossil fuels, and it's more efficient than corn-based ethanol gasoline. So ethanol-based gasoline is not a great one. The energy that's put into getting the ethanol is tremendous. When you factor in the fact that you're growing a crop, if you're doing it from corn, I should point out, you've got to grow the crop. You've got to harvest the crop. In growing the crop, all the tractors and all the planting and all this is energy. Sometimes we put down pesticides to get better yield. We have to use a lot of water, which is a precious resource. You then have to break down you have to strip the corn, break it down, and put it through these reactions. That is all energy intensive. And when you look at the net energy you get from ethanol, it's minuscule. So it's a poor choice for a future energy source, because you're using so much energy just to get it. And that's that whole energy idea. Biodiesel is a little bit better, a little bit more efficient. Another option is anaerobic biomass. We can get gases through anaerobic decomposition. So anaerobic should mean for you no oxygen. That's what anaerobic means. No or very low oxygen. Okay, I had it down here. That's what aerobic means. If you just get rid of the AN in the beginning, it's aerobic means oxygen-based. So here's an organic material. It's just meant to represent a general ratio of carbon to hydrogen and oxygen. It could be any organic material. But that is biomass's kind of common ratio, about 1 carbon to 2 hydrogens to 1 oxygen. So we always use that as kind of an example. So without oxygen, you get this right here, and you should recognize that as methane and a fuel source. Okay, that's a hydrocarbon from fossil fuels. That's natural gas. So that's one thing we can do. It's kind of nice. Okay, so some of the problems with biomass is cropland competition. So if you're doing like ethanol from corn, well, that's an important food. The cost of corn has gone up as a result of using ethanol. Water pollution, erosion, anytime you're growing stuff. The energy to produce it, the high water content. This is why I like generating, using waste materials. That I like. Or using crops that are not valuable food sources that can grow on land that we wouldn't normally farm. So if you notice, your book will talk about this too, like stuff like switchgrass. It's basically a weed. It's not something we use, but it'll grow without much water. You don't put down pesticide. It'll grow on land that corn won't grow or other crops won't grow. That's a great idea. But growing corn is a lousy idea. Okay, that takes us into solar energy now. Solar energy, we can use passive solar heating, which is just like a greenhouse. There's no storage, no circulation. When you open your windows to let the sunshine in the winter, that's passive solar heating. Now, you could go another step and make it active, and then you can kind of collect, store, and circulate. You can have pumps to move the heat. You can use water to store it. You heat up the water, then you can release it slowly, or rocks. And then use pumps to circulate it. That's all. This is pretty basic. You can read about it. Not going to spend much time on it. Take a look at your book. Figure 1611 is a good figure. But now we can generate electricity, because remember, electricity is something we always desire and we need. We want to be able to generate electricity. We use it for so much. So we can use active solar heating, where we heat a fluid, boil water. Oh, this is actually, and generate steam. So in an active solar heating system, water circulating through flat. No, this is wrong. Okay. This is not active. So this is thermal. This is out of place. Sorry. This is thermal. Here's active solar heating right here. Okay, here's where we're storing it. Okay, you're not generating electricity. You're just heating. Okay. So that's, I guess it's okay. It's just that word. That word is wrong. Thermal. It's thermal solar heating, and it really applies to this. So this active solar heating applies to this right here, and then we go into electricity from solar thermal energy. This is what this should be. Thermal solar heating. Active solar. This is not. Okay, I'm sorry. This is fine. I thought it said electricity. It doesn't say electricity. So as long as it doesn't say electricity, it's fine. Steam generation. This is fine. It's still heating. Okay? Still heating. Okay? No electricity generation. That's right. You can do, have a heat exchanger generating steam if you want. You can just pump hot water. This is not generating steam here. You can actually you can heat a fluid and get steam generation. Now this says electricity right here. So this is, I was correct. This is thermal. It says electricity. Active solar heating is just heating. Okay, so this is thermal solar heating, or electricity from solar thermal energy. In this case, you're generating steam. So you're just replacing coal or nuclear, whatever, with the sun, getting to cause steam generation. That's all. This one here is going to be a gas generator. All these others, you'll just be basically, here you go. Here's the parabolic trough. So this one right here, trough systems. And what we can have is we can have oil running through here. So yeah, I can't write on that because oil running through here, because then we can heat that and then carry that to water and generate the steam. Or you can basically use like molten salt there. What you have is these heliostats. You're just moving mirrors and concentrating the sun on this salt that gets really hot, and then you can use that to boil water. So you can either use the oil to boil the water to create the steam, or you can use like the molten salt, Or this one will be the gas generator. This is a whole built-in gas generator right there. So this one's the most efficient. Now, so the key, once we clarify this one more time since I messed it up, heating, you're not generating, so active and passive solar heating, you're not generating electricity, you're just heating. And this is active solar heating here. Electricity generation, we're going to use thermal heating, solar thermal energy. So we get rid of the word heating. Solar thermal energy or thermal solar energy. That's where you're going to generate the electricity, okay? So let's clarify that. Now we can get into generating electricity directly, not using, the heat of the sun, just using the energy of the sun. So these photovoltaic materials are semiconductors. And what a semiconductor is between a conductor and a non-conductor. When you think of a conductor, you think of a metal. It conducts electricity. Our wires are made out of copper because they conduct electricity. So you have conductors and insulators. Things like styrofoam don't conduct electricity, but they're good insulators. Glass, things like this, right? They don't conduct electricity. So you think about conductors, you think about metals. And you think about metals on the periodic table, you're looking about, remember, these are nonmetals over here. The blue are nonmetals. One word, but I didn't want to run out of space there. The green ones are your semi-metals or semiconductors, or metalloids, okay? There's silicon, which is going to be the basis for our semiconductors, and then hydrogen's blue also, and everything else is metals. So think about it, there's copper, great conductor of electricity, right? What do we make our heating pans out of, for cooking? We make them out of metals because they're great conductors of heat. We're interested in electricity, but conductors in general, good conductors of heat and electricity. Insulators are not good conductors. So these are somewhat in between. And silicon is the basis for most solar cells. So what happens is sunlight of sufficient energy can excite the electrons. And make sure you look at your book here, figures 16.8 and 16.21. Let's pull it up real quick. No, I went too far. Let's see where the solar is. 16.8. through 1621, 1618, I guess it was. Just showing you, they're basically some basic pictures. That's all these are. I thought it was shown. So your book doesn't actually, 8 through 21. That should be 18, I believe. Oh, it's for the whole section. 16. No, that's not. What figure's that? 1610. No, it should be 18 through 21. Yeah, it's really 1618 through 21. Okay, take a look at those figures. So what we have is sunlight can actually excite them. So let's look here now. Here's the solar cell design. This is some of the more advanced chemistry we'll deal with in this course in general. Here's a pure silicon crystal over here. Okay, now silicon actually has what we say 4 valence electrons. What that means is the outer electrons. So when we look at electrons, when you look at the periodic table is what I meant to pull up. The number of valence electrons here is just minus 10 here. You have to subtract 10 on this side of the periodic table. It's just the group number minus 10. So it's 4, 5, 6, 7, and 8. It's just the outer electrons. When you think about an atom, you think about the nucleus, right? And then you have these outer shells where the electrons are. Well, the most outer shell, those are what we call the valence electrons. And that's often all we care about in chemistry because those are the ones that are involved in bonding, in chemical reactions. So silicon has 4. I'm going to point out arsenic because it has 5. I'm going to point out gallium because it has 3. And let's go back to our chart here, our slides. Silicon has 4 valence electrons. So effectively, this silicon in the middle here, its 4 valence electrons are here. And then these other ones are shared from the neighboring ones, okay? Now, what we do is we simply do doping. This is the doping, where we periodically put in something that has extra valence electrons and something that has less valence electrons. Arsenic has an extra one. Gallium has missing ones, so effectively, that's out of place. It's supposed to be right here. A positive hole. Sometimes when I open up PowerPoint on my iPad, things don't match up right. So we create this kind of electron imbalance, and what that does, and this is called doping, by just replacing some of the silicons with these. What that does is allow us to, when the sunlight hits now, these electrons get excited. It allows us to create a current. There's very complicated chemistry here I'm not going to go into. But what you're doing is exciting electrons and then forcing them to move through an external wire as they kind of get excited and go to fill the holes over here, and you create layers, and this creates like a circuit. Okay? And this is what they ultimately look like. And we don't need to, you can look at these pictures. We don't spend a lot of time on these, but this is ultimately what they look like. And you can build them into panels, and then they can have systems that can track the sun. If you're just putting on a roof, you don't need that. But there's all different arrays you can make. And these are just some pictures where you see them. The idea of putting them on building sides and stuff like that, this is the type of thing that has to become more and more prevalent. Okay, I am going to do this in one video, so it's going to be a little bit long, but we're not doing too bad. I think we don't have that much left. Wind power is pretty basic. It's free and it's sustainable. You do need steady winds of 10 miles per hour or greater. I mean, you don't have to have that. That's for your best to get really good efficiency and to make it worth it. While no CO2 production, they're pretty efficient. There are some ecosystem issues, and that is some of the birds and bats have trouble navigating in them, and also the sound messes with them. Some people don't like the aesthetics, think they can ruin a countryside, something like that. I think they're kind of cool looking. And there is some used oil that you have to deal with that comes from the motors, but otherwise I think they're pretty cool looking. They're pretty good. And wind power has taken off. A lot of experts predicted that they wouldn't be that useful, and now it's becoming much more beneficial, and we're using them in areas that we thought the winds weren't, consistent enough or strong enough, and we're still getting good power generation. So in the beginning, this is kind of where we thought that this is really where the area where we can use wind power the most. But, we've got lots of wind power out in California now. So there are some alternative areas that we can use them in. Geothermal, this is basically harnessing the heat that's in the earth. And that heat's produced mainly from radioactive decay, but also leftover heat from, like, not leftover, but kind of latent heat from the Earth's core. We've got molten lava in the Earth, so there's heat there, obviously. But most of it's generated from radioactive decay. So you can pump water down there in pipes and then heat it up. Or you can draw water up that's hot, but those will have pollutants. No CO2, that's one advantage of it. So if you just pump hot water down and bring it back up, that's good. But if you're harnessing water that's underground that's heated, that you have to remove pollutants sometimes. So you got 3 temperature regimes. If you can get temperatures greater than 150 degrees C, then you can generate electricity. If you're lower than 90, then you're really just going to use like home heat pumps to power a heat pump. If you're 90 to 150, you can do some space heating. And this shows you some areas where geothermal's used in different temperature regimes. Most of it's out west. This shows you some of the plants. And these are some designs where you put these, slinky systems in the ground, piping systems in the ground. Here's an actual one. So you can harness that heat that's generated. And we can do things like tidal and wave power too. These are becoming, used a little bit more, but they're very limited where you can use them. You have to have certain tides, and you have to have certain currents to really make this worthwhile. This one's an artist rendition up here. All the rest are actual plants. Now let's talk about hydrogen to finish up. Many reactions involve the transfer of electrons. Okay, that's the principle of a battery. So we don't need to worry about where the electrons are transferring. That's for chemists to worry about. But electrons move, okay? And that's what chemical reactions are. They're kind of regrouping of atoms to share electrons differently, to transfer electrons from one species to another. This is the basis of a fuel cell, and a fuel cell is what's used was used in the space shuttles. Not to launch the rockets, to power instruments, okay? This is what a fuel cell was developed for. And they would take 3 fuel cells and put them in the space shuttles. In fact, if you watch the movie Apollo 13 with Tom Hanks, there's some lingo in there that refers to some of the problems they had. That's where they had some of the problems, one of the fuel cells. Or if you just read, about the history of that mission. So energy is released in this process. They're clean reactions. You get water out of it. In fact, the astronauts were able to use this as a potential drinking water source. The problem is this right here. Its source is problematic. Where do you get it from? If you get it from coal and natural gas, you do it in a controlled environment. You're not burning it, but you still have lots of CO2 production. You still have energy needed to get that. So it's not a good net energy. Storing of hydrogen is difficult. It's kind of burns invisibly. It's a gas, so you have to store it as opposed to a liquid. So it makes it difficult for transportation as a source, and also to transport it to different regions of the world. Gases are always problematic because they take up so much space, and if you condense them, it takes up a lot of energy. Now your book, and here's kind of the working of that fuel cell. Hydrogen coming in at one end, oxygen coming in at the other end, and then you got these electrons being generated. That's how we get the energy. Just force those electrons to go out through a circuit, no different than a battery. You're forcing electrons, instead of going from reactant A to reactant B, you force it to go through a circuit first in going from A to B. And here's an actual fuel cell. Okay, and I corrected this before I started this video. For some reason, it's no longer corrected. This tidal wave power thing is in the way in this slide. But anyway, your book, downplays this a little bit. The key is that how you generate this. And if you get this from solar energy, so one thing we can do is we can take water, allow the sunlight to come in, and we can split the water and get hydrogen gas. If you do that, then it's worthwhile. Not getting it from this. And then you generate it right on site and use that hydrogen to generate electricity. That's the way hydrogen needs to be generated and utilized in this country and in the world to make it a worthwhile source. And then you can put fuel cells at people's houses. You can even put fuel cells in cars. It's a little tricky because hydrogen is very flammable. That was the Hindenburg, of course. Hindenburg that caught fire as a result of hydrogen gas. So, ultimately, I wanted to end with conservation and saying that a lot of people don't think this makes a difference, but it really does. We have tremendous amount of energy waste. I showed you at the beginning in the book that 41% of energy is wasted due to inefficiency. Well, conserving that makes a big difference. So it is very important. This is showing cost and capacity for renewable energy. Capacity is the amount that you have. So you see photovoltaics there. Cost has come down a lot. This is a little bit older figure. And we're only using 21 to 21.6% of our basically capacity. And it's come down a lot in cost. When you look at fossil fuels, they're like a penny or two to compare. Hydroelectric's pretty low, goes down to about 4 cents. But largely that's because we don't account for the cost of mining it and raping the land and causing all this environmental pollution, number of people that die prematurely from asthma, from air pollution, and all of this. But these costs are coming down tremendously. That's much lower. In fact, down here you'll see photovoltaics cost in 2020 only 9 cents. Now, this was 18 to 43 cents, already down, predicted to come down to about 6.9. At this point, there's no reason not to use renewables anymore because they're pretty cost efficient. You look at what we can do with biomass if done right and using the right types of materials. This is one that, I'm sorry, that's concentrating solar power. Here's photovoltaics here. Still about 9. This is pretty useful too. This is just using the sun to heat the liquids. And it's actually a pretty useful, simple engineering that we can do now and do more of. But using coal, what's called clean coal, is still not that great, okay? It's going to be costing as much as solar, so why bother? Because coal is a precious resource that we can use to make materials from, right? Use under specialized circumstances. Wind is pretty cheap, right? So geothermal, and a lot of these are limited. You can only use geothermal in certain areas, wind certain areas. But that's okay. Use wind where you can use it. Use geothermal where you can. Solar, same thing. You've got to have sun. But we're doing a better job of actually storing that energy, and that's one of the keys to making solar energy usable is really learning how to store it. So those areas that don't have sun, we've got to use wind. If they don't have sun or wind, we got to use biomass, okay, or hydroelectric. Nuclear, a lot of people like nuclear to bridge this gap and get us away from CO2 production, and that's okay. It could be continued to use nuclear. I don't think we should be building new plants. Continue to use the existing plants and slowly phase that out as we make these transitions. So here's your summary that gives you an idea of what to focus on in studying for the exams, and that concludes the video. So we'll talk about this in our next class. And that ends the video.